Hey everyone, welcome back. So this is part 2 where we'll prove the following theorem. And in part 1, we defined some of the words on this slide. So if things don't make sense, maybe go back. But just recall that for shorthand, we'll say that a knot in S3, if it has the property that all of its branch cyclic covers are L spaces, we'll call it a branched L space knot. And the theorem that I want to tell you about today is that these knots pictured on the side have this property. So all their branch covers are L spaces. We also pointed out in part 1 that, that they're slice and some of them are quasi-positive, and this answered a question of Boileau, Boyer, and Gordon, but I'm not going to show that they're slice or that they're quasi-positive in this talk. So let's recall a useful theorem of Boschbach and Sabo, which says that if I have an alternating knot, the double branch cover is an L space. The problem for us is that the knots that we're considering, they're not alternating. So we don't even know that the double branch cover is an L space. And of course, we're interested in higher cyclic branch covers also. So we have these two problems, which is that we don't even know that the double branch cover, which is in general easier to answer this question for. And what about higher branch covers? And I'm going to first focus on this second problem, and we'll come back to the problem of this non-alternatingness. Okay, so we're going to use a property that some knots have called periodicity. So in S3, a periodic symmetry is a certain type of rotation. So I have an axis, which is always a circle, and I rotate about it by an angle of 2 pi over n. And how that relates to knot theory is, of course, knots are sitting inside of S3. And so if they behave nicely with respect to the symmetry, we'll say that the knot is also periodic. So we want that the axis of the symmetry is disjoint from the knot, and also that the symmetry takes the knot to itself. So in this picture, we have a knot, and this green dot is supposed to be the axis of the symmetry in the plane. So if I take this diagram and just rotate it 180 degrees, it's taken to itself. And the axis in all of S3 is just some circle, and it's not going to intersect the knot. So this is a 2 periodic knot. And whenever we're in this situation of having a 2 periodic knot, we can use the following construction. So this is a well-known construction. It was used by lots of people. I'm not quite sure who to attribute it to, but it dates to the 1980s. So here's our 2 periodic knot. It's actually the figure 8 knot. And here's its axis I've drawn actually as a circle and not just a point in the diagram. So this is just an isotopy so that the axis doesn't go through the point at infinity. So that's our knot with a 2 periodic symmetry. And if I take the quotient of the symmetry, what I get back as a 3 manifold is S3 again. And the black curve is the quotient of the knot, and the green curve is the quotient of the axis. So since we're in S3, I still can draw a diagram of this picture. And in fact, this is a branch covering map. This is, if we look at what's happening away from the green curve, it really is just a rotation. It's a covering. And of course, the lift of any point on the green curve is just 1 point. So it's not actually a covering map, but it is a branch covering map. Okay. And the manifolds that we're interested in are the n-fold branched covers of the figure 8 knot in this case, so the black curve. And so what we've kind of said on the left-hand side of this picture is that we can think of the n-fold branch cover of the figure 8 knot as this composite branching. So first 2-fold branch over the green, then n-fold branch over the black curve. And what we're going to start doing on the right-hand side of this picture is just change the order of those 2 branchings. So we'll still n-fold branch over the black and 2-fold branch over the green, but not necessarily in the same order as before. So here on the right, what I've done is n-fold branch over the black curve first instead. And I'm not going to tell you how to get this picture. This green curve is supposed to be the lift of the green axis under that branching. And the reason I can even draw a picture for you is the fact that this black curve is actually unknotted. Maybe you can see it from the diagram, which lets us know that once we end-fold branch cover over it, we're still in S3, so we can still draw diagrams of knots. And so this lift of the green axis is what I'll call L sub n. So it depends on n, the index of the branching. So here in this picture, n is 4. And finally, I want a 2-fold branch over the green. And the statement is that I get the same thing as if I'd gone up the left-hand side of the diagram. Okay, so what have we just done? We've just shown that the end-fold branch covers of a 2-periodic knot. It was important that the quotient knot was unknotted. But when that happens, those manifolds are also 2-fold branch covers of some other link in S3. And what I claim is that this shows that the figure 8 knot is a branched L space knot. So these knots, all of whose branch cyclic covers are L spaces. And why is that? So here we have the ln on the right again, and in this particular example, n is 4, and if maybe you can see from the diagram that it's an alternating diagram. But in fact, if n is not 4, this picture will look very similar. So in this example, it has a 4-fold symmetry, but in general, it'll have an n-fold symmetry, and the pattern that you see repeated 4 times here will be repeated n times, and you can check it'll still be alternating. Okay, so just to summarize, we found a 2-periodic symmetry for the figure 8 knot. We noticed that the quotient was unknotted, and then by some procedure that I didn't explain to you, we found a link for each n whose double branch cover was the n-fold branch cover of our original knot. And then the last thing you want to know is that double branch cover in L space. Are we any closer to understanding whether these manifolds are L spaces? And in general, that's hard. So right now, I've only told you one theorem that can answer that question, and that's if this link is alternating. Okay, so back to the pretzel knots that we're interested in. So each of these knots have a 2-periodic symmetry. So it's the first step to kind of running the procedure that we just described. Here it is. The axis kind of goes, between the first crossing through the twist box and through that last crossing on the right. And my drawing maybe doesn't make this clear, but it's not intersecting the knot anywhere. And if I kind of rotate 180 degrees into the plane, I'll get the same diagram back. Okay, so the problem again is, the only thing that we have at our disposal right now is that the double branch cover is an L space for alternating knots. We took care of this problem that the index is larger than 2, so we've turned our problem into a question about double branch covers. But we still have this problem that the pretzel knots that we're interested in, and also these related links whose double branch cover is the pretzel knot. It turns out they're not going to be alternating. So let me just show you that. Okay, so by a similar procedure to the figure 8 knot case, we get this link. It depends on 2 parameters, the index of the branching and the number of twists in the pretzel knot. Here it is in a cylinder. So it's not a knot. It's just a bunch of strands in a cylinder. But if I kind of close up the cylinder, kind of as you would a braid, I'll get a closed link. So those are the links that I'm talking about. And the claim is that their double branch cover is the n-fold branch cover of one of these pretzel links. So these are the links that we want to know whether their double branch covers are L spaces. And just to put that, this picture kind of overlaid on the picture for the figure 8 knot, right? We started with the pretzel knots, we found the symmetry. Here's the quotient, and by some mysterious procedure that I didn't explain to you, then I get these ln sub k. So here on the right is an example if n is 4. And so if I take the double branch cover of that, I'm supposed to get the n-fold branch cover of, so in this case, the 4-fold branch cover of whatever pretzel knot. And maybe you can see in this picture, at least this diagram is not alternating, but in general, these ln sub k's are not alternating. So we need something stronger than this Ojva-Szabo theorem that I told you about. And we're gonna need a generalization of alternating too. And before I can tell you what that is, I have to tell you about resolving a crossing in a diagram. So let's say I wanted to get rid of this crossing for some reason. I just want to destroy my diagram. But I don't want to destroy it too much. So I still want to end up with a link diagram at the end and not have just a bunch of lines on the page that don't connect to each other. So there's kind of 2 natural ways to do that are called resolutions. The first one, I connect the left 2 strands to each other in kind of this boring way, and I connect the right 2 strands to each other in this boring way. Another way I could do it is connect the top 2 and the bottom 2. Okay, so these are called the infinity resolution and the 0 resolution. So I keep outside of the circle, I keep everything the same. I've just changed kind of this crossing region, and I've reduced the number of crossings in my diagram by 1. So I've made the diagram a little simpler maybe. Okay, so that's a resolution of a crossing. And the generalization of alternating that we'll use in the proof is due to Kriz and Kriz. And those are called weakly quasi-alternating links. And they're defined inductively. So I start assuming that the unknot and unlinks of multiple components are in this set of weakly quasi-alternating links. Those of you that know what quasi-alternating is, the difference here is that we allow unlinks of multiple components. Okay, and so once I know those are in my set, how can I get more? Well, I also know that a link is in this set if there's some crossing in some diagram I can find where when I resolve it, I know that both of the simpler diagrams were already in my set. So L0 and L infinity were already in Q. Okay, and then there's some technical condition about the determinants of the link, but it's not going to come up in this talk. And it's not obvious from this definition, but alternating knots satisfy this property. So this is definitely a generalization of alternating. But there are new knots that we're getting. There's non-alternating knots, which are weakly quasi-alternating. For example, are pretzel knots. And the reason this is a nice generalization of alternating is that we still get this theorem that looks a lot like our Ojva-Szabo theorem. So Kriz and Kriz showed that the double branch cover of a weakly quasi-alternating knot, and it's important that it's a knot and not a link of multiple components, that is an L space. So one hope would be to take our links that we're interested in their double branch covers, and we could try to show that these links are, well, first of all, they need to be a knot to use this theorem, and they need to be weakly quasi-alternating. Okay. I'm going to focus on the weakly quasi-alternating question. It's not so hard to show that they're actually knots. You can check, because it's like this repeated pattern, you can just check that it's connected up to a connected one manifold. Okay. So if we want to show these links are weakly quasi-alternating, we should find a crossing to resolve. And the one I'm going to choose is in a particular crossing box. So for example, this is an example where n is 4, you can see the 4-fold symmetry, and 3 is the number of twists in each region. Okay, So I'm going to choose this crossing to resolve. And I have two choices. The first one I'm going to choose is the zero smoothing or resolution. So I got rid of that crossing. And something kind of magical happens, which is I can start untwisting, and I end up with one unknotted component. And the rest of the diagram really just kind of unravels. Start untwisting, pulling through, and you can kind of see this kind of repeats in each of the kind of n repeated pieces of the knot. And what I get at the end is just two unlinked unknots. And we know that that is weakly quasi-alternating. So, okay, we did something. What did we do? We showed that L0 is weakly quasi-alternating. So we would also want to show that L infinity is weakly quasi-alternating. Right, so we need to do the other resolution, and nothing as magical happens in this situation, but we did at least reduce the number of crossings of our diagram by 1. Okay, so what if we just did that everywhere? At each of the twist boxes, I always do the infinity resolution. Well, I get a diagram like this, and this diagram isn't alternating, but if I do an isotopy, so I just kind of drag some strands around, I actually do get an alternating diagram, which is nice because alternating links are weakly quasi-alternating. Okay, so are we any closer? So yeah, we are, but we actually need to use induction. So our base case is going to be the case where there are no twists at all. So when k is 0. So that was this picture here, which we simplified here. Okay, so our base case is weakly quasi-alternating. And anytime I take my link ln sub k and resolve, I either get, if I do the 0 resolution, I get the unlink of 2 components. And if I do the infinity resolution, depending on so I reduce the number of crossings by 1, and depending on the sign of k, I've either added 1 or subtracted 1 from k, but I've made my knot simpler. And we're inducting on the total number of twists, so that takes us by induction into something we understand. So this is weakly quasi-alternating by induction, by the inductive hypothesis. And this we just know is weakly quasi-alternating. Is one of the base cases that we know that the unlink of 2 components is weakly quasi-alternating. So induction gives us the statement that we want. Great. So again, our goal is to understand the n-fold branch covers of this knot on the left, but what we've actually done is show that this knot on the right is weakly quasi-alternating, and so its double branch cover is an L space, which means that all these n-fold branch covers are also L spaces. So these pretzel knots have this property that we want. Okay, so this was a lot of work, but it really only worked for this specific infinite family. So one of your questions might be, can this idea work for other links? And well, in some sense, it does work, for example, to reprove this theorem of Peters and Tarragaido about 2 bridge knots, but can you get any new results? So that's a great question. I'm working on that. And the second obvious question is, can you build knots that give you all of these L spaces via branch cyclic covering that don't have a 2 periodic symmetry? So do any exist? And if they do, how would you find them? This kind of procedure that we illustrated obviously won't work for those. So let me end there, and I hope to see you at some other events. Bye.